Hi, my name's Nate Hartnett. I'm a material science student from UW-Eau Claire. The title of my work is Characterization of Damage Induced on REBCO Superconducting Tape by Mechanical Slitting. So, an introduction to superconductors. A superconductor is a material that can conduct electricity with no resistance. In other words, there's no loss of energy due to heat. And they're used to create strong magnetic fields. So superconductors are used in fusion reactors, which are the future of energy in the world because they're capable of producing limitless energy with basically no emissions. Rare earth barium-copper-oxide or REBCO superconductors are a specific type of superconductor that are comprised of several layers. And if you look at the bottom right image, that's a picture of a fusion reactor that's designed using REBCO coils. Or REBCO coils. So the motivation for our work, so REBCO superconductors are superior to any other superconducting wire because they have better superconducting properties. If you look at the top right graph, you can see the top two data sets, UH R&D short tape and SPI commercial tape, are both REBCO superconductors, and they're above all of the other competing superconductors. So that sounds great and all, but what's the downside of them? Well, the downside is that they're pretty mechanically frail and they're prone to delamination. So you may ask, why do they delaminate? Well, when they're produced, they're cut by a mechanical slitter, and this causes cracking on the edges, and then those cracks can initiate delamination. So in this study, we're investigating the formation of those cracks based on the geometry of the slitter. So the samples provided to us were fabricated as 12 millimeter wide wires, and then they were slit by superpower into 6 2 millimeter wires. If you look at the top right diagram, you can see the sort of copper colored wider wire being slit into 6 different shorter ribbons or less wide ribbons. And then you can also see how we labeled ours based on number. So 1, 2, 3, 4, 5, 6. We used scanning electron microscopy or SEM and confocal laser microscopy for this study. The SEM was used for mostly qualitative analysis just to see what was going on. And then we used the confocal microscope for digital image analysis to measure the fracturing we see. So looking at all the edges of the samples, we noticed 2 different damage patterns, as you can see on the bottom right 2 images. The narrow damage, where none of the REBCO layer was fractured off, and the wide damage, where, as you can see, the wider layer is the REBCO, and then the darker part is where the REBCO is fractured off because of slitting. And those were called narrow and wide damage. So from the SEM images, we noticed that all of the odd samples, so 1, 3, and 5, as you can see on the top right figure, showed wide damage, and the even samples showed narrow damage. This is also confirmed with digital image analysis, where we measured the length of the fracturing in each sample, and you can see that in the bottom left graph. So the y-axis is the fracture length, and the x-axis is the sample number. So the blue ones all showed high fracture lengths, and the green ones showed low fracture lengths. So the odd-even trend, we believe that is due to whether the REBCO layer is in tension or compression. I guess first I should have you take notice to the schematic provided on top right. So this is what the REBCO wire looks like, all of its layers. Most important layers for this study are the black layer, which is the superconducting layer, and the silvery, the silvery thicker layer, which is the Hastelloy layer, and basically that's the backbone of the superconductor. So if you look at the two images below that, in the even samples, the wires are being bent. So the black arrows are representing the blades of the slitter, and it's pushing each side of it up so that the bottom of the conductor is in tension and the top is in compression. So the bottom layer, which is the Hastelloy layer or the backbone layer, is in tension, and then the REBCO layer is in compression for the even samples, and vice versa. And when the REBCO layer is in tension, that's when the wide damage is occurring. So then to validate our results, we did the exact same study, but we flipped the conductor when it was being slitted. So the REBCO layer is on the bottom when it was being slitted. So for the even samples, that would mean that it's in tension. So we would expect the even samples to show wide damage instead of the odd samples, and that is what we observed, which is a pretty significant result, and it means that we can control the damage produced during slitting if we can control the strain state of the REBCO during slitting. So in our future work, we'd like to continue to work with superpower to develop a new method for slitting and then test that method with the same study. So I'd like to thank Matt Jewell for letting me do research with him, Javier Ramirez for collecting some of the data and working with me, Yifei Zhang from Superpower for providing the samples and working with us. And this study was funded by DOE and Department of Energy and NSF. And then I'd also like to thank the Materials Science and Engineering Center at Eau Claire for letting us use their instrumentation. Thank you for listening.